We're now going to revisit an old friend, right? One from Calc 2, your second semester of calculus. We're going to talk about arc length. And what we want to be able to do is essentially convert what we know about arc length over into like a vector form. So suppose we wanted to find the length of one of these vector curves, right? Again, just let's say here's our vector curve. And again, this could be a curve in 2 or 3 dimensions, and all we have is the vector function that defines this curve. We want to know how long is this curve, right? So how long is r of t? And let's say we know that it goes from, or the curve is defined for t going from, let's say, t0 to t1. Right? So how long is that curve? Well, let's take a step back and see what we know about arc length, right? So if y equals f of x is differentiable, right? So if y equals f of x is differentiable on the interval a to b, then the arc length, or the length of this curve, so then the arc length of y equals f of x is given by this formula, right? So it's the integral from a to b, you might remember it, it's a square root of 1 plus the derivative squared, all under the square root, and then you integrate that with respect to x, right? Now, the thing that you integrate, this is called the arc length differential, right? In other words, it's the very, very small lengths along this curve, the infinitesimally small lengths that the integral kind of sums up to get the length of the full curve. So we call these arc length differentials. So I want to focus on that part of it to see if we can somehow convert this into a form where we can express it like, what if we were to convert this function and get it into like a parametric form, right? And then in a vector form, then we should be able to restate this formula in vector form as well. So let's see if we can do that. Now, if we go back a step further, right? So if we go back a step further and we say, suppose x and y are both differentiable functions of t, right? Are both differentiable functions of t, right? So this goes back to essentially related rates, right? So, but I'm not going to treat it like a related rates problem. Basically, if I know that x and y are both differentiable functions of t, what I can do is I can write dy dx as this. I can say in other words, I can do a little algebra, and if I divide the top and the bottom by dt, so if I do dy dt over dx dt, it's the same expression, right? It's just that now I have a derivative with respect to a derivative of y with respect to t on top, and then a derivative of y with respect to t in the denominator. So what I'm going to do is do a little bit of algebra with this and see if we can express this arc length differential now in terms of t. Because if I can do that, then it means I can relate it back to these vector functions. All right, so therefore, if I take 1 plus dy dx squared times dx, well, let's see what we can do. Let's go ahead and where I have dy dx, let's replace it by this expression, right? So under the square root, I will have 1 plus, and then I'll have dy dt over dx dt all squared. And then this is times dx. All right. So now what I have a fraction being squared, so I can square the top and I can square the bottom. So let's do this. So 1 plus dy dt squared over dx dt squared, and I still have my dx there. Now I am adding what is, two fractions, right? So I can get the common denominator, which is, so let's do this. So I'll have the square root, I'll write that a little bigger. So then my common denominator is going to be dx dt squared. And then this, I'd have to multiply this by dx dt squared. So I'll have a dx dt squared plus dy dt squared. And that's all under the square root, and then I still have my times dx there. All right. So what's going to happen? Well, now I have the square root of a single fraction, so I can take the square root of the top and then over the square root of the bottom. So I can take the square root of dx dt squared plus dy dt squared over, but then when I take the square root of the bottom, since the bottom is a perfect square, the root is going to go away. So I'm going to have dx dt and then times dx. All right. Well, things are looking a little bit better now. So if we think about it, what I have here is I have dx dt squared plus dy dt squared. Now I am dividing by dx dt, which again, if I treat this as a fraction, which technically it's not, but if I can manipulate it like a fraction, dividing by dx dt is the same as multiplying by dt dx. Multiply by the reciprocal of the denominator, and then I still have my dx there. So then the dx's cancel out, and now I have a new form of my arc length differential. It's the derivative of x with respect to t squared plus the derivative of y with respect to t squared times dt. So this now is the arc length differential if I have my function, or x being a function of differentiable function of t, and y being a differentiable function of t. If I integrate this, it will give me the arc length of now a parametric curve. So essentially we've derived this theorem. So this is what we will say. So now I'm going to state everything in vector form. So if r of t is now given by x of t, y of t, right? So if I now have it in this vector form where my x component is a function of t, y component is a function of t, and let's say r of t is smooth, so, and r of t is smooth, and again, we know what that means, right? So it means our derivatives are continuous, and they're never going to be simultaneously equal to zero. So I'll never run into an issue where I might have a zero in the denominator. As long as I assume that my vector function is nice and smooth, then the arc length, so the arc length of r of t for, and let's say t going from t0 to t1, right? That the length of that curve is given by, and then here's our arc length formula. So the integral from t0 to t1, yeah, integrate your arc length differential. This is now just the parametric form of the arc length differential, and this is our formula. So the square root of dx dt squared plus dy dt squared, all of that integrated with respect to t, right? So going back to Calc 2, we've now taken a concept from Calc 2 with a sprinkling of a concept from Calc 1, and now brought it into this sort of vector realm, right? But what's nice is we can take it further, because remember, once we have the concept of some most vector calculations in R2, it will translate very easily to vector functions in R3. So if I now have a third component, so let's say my z component is also a function of t, then I can extend this pattern and get another formula, right? Or a formula for the arc length of a function in 3 space, right? So I'll just state it as one big theorem. So similarly, forgot on L. So similarly, if r of t is this function, x of t, y of t, z of t, and r of t again is smooth, right? Then I'll just so it's the same interval, right? Same notation. I'll just write down what the formula is. So then the arc length, again, over that interval is equal to the definite integral from t0 to t1. What do we integrate? The square root of dx dt squared plus dy dt squared plus dz dt squared, and then we integrate with respect to t, right? Again, we're seeing another formula where the arc length, or I should say the idea of once you establish the pattern or the formula in, say, R2, you can translate it quite easily to R3. Now, I'm going to use the R3 equation to restate this in a more compact form. So let's take a look at what this is saying. It's kind of interesting when you look at this, what this formula requires. I see a square root, I see quantities being squared, and I see a sum. That to me looks like when you're computing a certain magnitude. So it almost looks like this expression that you're integrating, this integrand, is this a magnitude of something? You know, is this a magnitude? What could it be the magnitude of? Well, look at what you're squaring. You're squaring first derivatives. You're squaring the derivative of this function, the derivative of this function, and the derivative of this function. Well, if I were to differentiate my r, right? If I were to differentiate my r, that would give me my tangent function, right? So since, let's write that down. Since r prime of t is equal to dx dt, dy dt, dz dt, right? If I now said, well, what is the magnitude of my tangent function? I would get exactly that expression that I have boxed in red, right? So since that's the case, the magnitude of r prime of t, I'm sorry, the derivative of, well, I said prime, right? Okay, so the magnitude of r prime of t is equal to dx dt squared plus dy dt squared plus dz dt squared. That means I can restate my arc length formula in a much more compact, a much simpler way by simply saying that the arc length of a vector function is the definite integral of the magnitude of the derivative of that vector function. So therefore, since this, and we have the following alternative formula for L. It's not like a different formula, like, a different way to compute arc length. No, arc length is always going to involve, integrating the square root of, the sum of squares, something like that. Alternative meaning it can be expressed in a slightly different way. So it's the integral from t0 to t1 of the magnitude of the derivative of your vector function, right? So there we go. So a nice formula for arc length, right? Let's do an example. All right, so let's try this one. So here's an example. What is the arc length of the curve given below? And here's our curve again in vector form. So first component is 1/3 t cubed, second component 4t, third component root 2 t squared. And again, this is not enough, right? Since we're going to set up a definite integral, we need to know what range of values of t define this curve. Well, let's say t goes from 0 to 2. There we go, right? So first thing we're going to have to do, so I'm going to, let's find r prime of t, right? So let's find r prime. So this is our tangent vector. So differentiating 1/3 t cubed gives me t squared. Differentiating 4t gives me 4. Differentiating root 2t squared gives me root 2 over 2t, right? So this is my tangent vector. Now let's compute the magnitude of this tangent vector. So the magnitude of r prime of t, what are we going to do? We're going to square each component and add, and then take a square root. So let's square first. So we got t to the 4th, and then plus, we got 16, plus, now when I square this, and because this is these two factors are being multiplied, I'll get 2 over 4, so that's 1/2, right? T squared, right? And then I have to compute that. So, oh, wait a second. I just looked at, I think I made an error here. Why did I divide by 2? I should multiply by 2. Yeah, so it is the third component of the derivative is 2 root 2t. There we go. So then when we square this, this will give me 4. This will give me 2, so that's 8t squared, right? When I square the third component, and then I have to compute the or the square root of that. So if we write that in kind of the standard form of the fourth degree polynomial under the root, it's t to the fourth plus 8t squared plus 16. Now, keep in mind, this is something that we're going to have to integrate. So we know integrating square roots can be tricky, but if we look carefully, under the square root, it's actually a perfect square, right? And just like in Calc 2, many of those problems were set up so that even though it might look a little messy at the start, there is a perfect square under here, because t to the fourth plus 8t squared plus 16 can be written as t squared plus 4 all squared. If I FOIL this out, and I encourage you to try and do it, if you can't really see it, write it out, FOIL it out, collect your like terms, you're going to get back the t to the fourth plus 8t squared plus 16. And then I am taking the square root of a perfect square. And since t squared plus 4 is always non-negative, in fact it's always positive, it's strictly greater than 0, then the square root and the square cancels each other out, and then I have, or cancel each other out, and then I have t squared plus 4, right? So this is the magnitude of the tangent vector function to my original function. And to find the arc length now, we have to integrate this from 0 to 2. So the actual integral isn't going to be too bad at all, right? Because we've done all the work in terms of the algebra and the simplifying. So our arc length is the integral from 0 to 2 of this thing, t squared plus 4 with respect to t. So now we integrate, and we have 1/3 t cubed plus 4t, and we evaluate at 0 and at 2 using our fundamental theorem. At the upper limit, what do we have? 8/3 plus 8. And then at the lower limit, we have 0. Yep. So then this is 8/3 plus 24/3 for 32/3 units of length. And there we go, right? So the big step now is that we have a way, right, of finding the length of these curves. And you might wonder why is that important? Well, it turns out there are applications related to motion that we're going to look at very shortly, where we'll be doing this sort of calculation, finding another quantity. We might not refer to it as arc length, but that's essentially what we're going to be finding. So it's important that we understand how to set up and evaluate problems like this, because we're going to be doing that some more in the future. So sure, I'll see you then. Bye.